Have you ever asked yourself, why is it easy sometimes to pull a spring while other times or other types of springs it's very difficult? Well, to answer that, watch this video. Hello everybody and welcome. Today we will be talking about spring forces. Now, when you pull a spring, it will stretch. Now, the amount of force needed to stretch this spring depends on two main things. The first thing is how long I want to stretch this spring, and the other thing is how strong this spring is. So we have some springs that are hard and difficult to stretch, and we have some springs that are weak and easy to stretch. Now, every spring has a certain strength called the spring's constant. Now the spring's constant, in other words, it's the spring resistance to deformation. So if, for example, if I have two springs, if I have a small weak spring and I have a spring that is very thick and strong, I can say that this spring has a spring's constant that is higher than this spring because it is harder to pull or deform. Now, if I want to find the force that is inside the spring, I can simply use a simple equation saying that the force inside the spring is equal to K multiplied by delta L. So imagine here that this is the spring when it's unstretched. So it's not stretched yet, okay? Now, if I stretch this spring, I will apply a force to stretch this spring. So when I stretch this spring for a small distance, I'm applying a small force. But if I want to stretch this spring for a larger distance, I will need to apply a higher force. So I can simply say that it's equal to K multiplied by delta L. So Fs, it's the force inside the spring. K is the spring's constant, and we talked about it before. And finally, delta L, it's the change in the spring's length. It's not the final length of the spring. It's the change in the length of the spring. Now, before we go on to solving some problems, it's very important to take these things into consideration when finding the force in a spring. The first thing is use the change in length of the spring, not the new final length. In other words, if a spring was originally 1 meter long and was stretched to become 1.1 meters, the change in the length in this case is equal to 0.1 meters. The other thing is that you need to keep in mind the consistency of units. For example, sometimes the spring's constant, it's given in newtons per millimeter instead of newtons per meter. In this case, delta L must also be in millimeters. So I must look at the unit of the spring's constant, and I must keep delta L in the same unit, okay? Now, the scientist Robert Hooke was the one who discovered this relationship, and he said that the size of the spring's deformation is proportional to the applied force considering the elastic limit is not exceeded. In other words, when I say the word proportional, this means if I stretch it more, I will apply more force. So the more I stretch, I am applying more force. But it's very important to keep in mind that considering that the elastic limit is not exceeded. What's the elastic limit? Well, all the springs have something called the elastic limit. You will keep on stretching the spring and it will go back to its original position. Then you stretch it more and it will go back to its original position. At a certain moment, if you pull it too much, it won't go back to its original position. Some may say that the spring is now broken. Well, it's not broken. What happened here is that it exceeded its elastic limit. It won't go back to its original shape because now it is deformed. Now, Hooke's law can be represented graphically using this simple relationship. Here we have the force inside the spring in the y-axis, and here we have the change in length. So if I would ask you, what would the slope represent? Okay, let's look here at the slope. We know that the slope is equal to delta y over delta x. What is in the y-axis? I can say that what's in the y-axis, it's the force inside the spring, and what's in the x-axis, it will be delta L. Well, this can only give me the spring's constant K because I know that Fs is equal to K multiplied by delta L. So if I divide both sides by delta L, I will get that K is equal to Fs divided by delta L. Now, let's look at this very easy example. Find the force inside the spring if it had a spring constant at 0.5 Newton per millimeter and its length increased by 10 millimeters. So I can simply say that the Fs is equal to K multiplied by delta L. K is equal to 0.5 newtons per millimeter multiplied by 10, and we look here that the spring's constant is in millimeters and the length is in millimeters, so I can simply say that I need 5 newtons to stretch this spring by a distance equal to 10 millimeters. Next question. It says here that a spring had a length of 0.05 millimeters before it was stretched. A force of 10 newtons was applied, causing it to stretch. The length of the spring became 0.08. Find the spring's constant. Fs is equal to K multiplied by delta L. I can say in this case that K is equal to the force inside the spring divided by the change in length. Again, the change in length. So I can say that K is simply equal to the force, which is 10, divided by the change in length. Well, the length was 0.08. Now it's 0.05. So I can say that the change in length is 0.03. This gives me a spring's constant K equal to 333.3. It's important to keep in mind that the unit here was newtons and the unit here was millimeters. Look at the question, it's millimeters, so I can say that the unit is newtons per millimeters. As I said, the consistency of units is very important. Let's look at this next question. It says here that a spring meter reads 20 newtons as it pulls a 5 kilogram mass across the table. So let's look at this. This is the spring we have. Okay. And it has a reading saying that it's being pulled by a force equal to 20 newtons, and it has a mass right here that's equal to 5 kilograms, okay, on a table. What is the force exerted by the mass on the spring? Well, actually the 5 kilogram here is nothing. It's just asking me, in other words, do you know that if you apply a force on the spring that's equal to 20 newtons, this will cause a force inside the spring equal to 20 newtons? Well, actually we already know that because we covered it when we talked about Newton's third law. Every action has a reaction that's equal in magnitude and opposite in direction. So I can simply say that the answer is B, and the 5 kilograms has nothing to do with our question. Next question. 4 identical springs evenly support a steel block of weight W. The elastic constant of each spring is K. Which expression gives the distance of compression from equilibrium? Okay. Now I can say that the force inside the spring is equal to K multiplied by delta L. Now he's asking which of these expressions will give the distance. So I can say that delta L is equal to Fs divided by K. Now, what is the force and what is K? It says that this block, let's draw it right here, it's being supported by 4 identical springs, right? And it has the weight of W. Well, I can say simply that since these springs are identical, each one of them will be carrying, let's look at this one right here. Let's draw it again right here. It will be carrying a force equal to W over 4. Why over 4? Because it's going to be distributed along these 4 springs, okay? So if I need to find the force is equal to W over 4 divided by K, which is the spring's constant. So if I go back to the equation, I can say that delta L is equal to W over 4 divided by the spring's constant, which is K, and I can rewrite it again. I can say it's the same as W over 4K. So the answer here is going to be C. I hope it's clear. Next question. It says here that as shown, a brick of mass M is hung from a spring that has a constant K. When hanging at equilibrium, in other words, it's not moving, the spring is stretched a distance x. Which of the following is the expression that gives me the distance x? Well, again, I know that Fs is equal to K multiplied by delta L. Now he's saying that the distance, he's calling it x, so I can just say that delta L, or in other words, x, it's going to be equal to Fs divided by K. Or in other words, x is equal to Fs divided by K, because he's naming delta L as x. Well, I need to know the force so I can find the change in length. Well, remember that the spring is carrying a mass equal to m. And we learned from the previous video that any object that has a mass is affected by a force called weight. And this force is equal to the mass multiplied by the gravitational acceleration. So I can simply replace this force by m multiplied by g. So I can say that x is equal to mg divided by k. Let's see our choices. We can see that the answer is simply D, mg divided by k. Now we have a good idea on how forces are created in springs. Stay tuned in the next videos. We will be introducing other types of forces. See you then.